In the last video, we saw that the fact that all observers agree on the same speed of light requires us to revisit our assumptions about simultaneity and how different observers are experiencing distance and time. To wit, we saw that moving meter sticks are short. It looks short to someone who sees them as moving, and moving clocks looks like they're running slow to someone who sees them as moving. Now, in that video, I pointed out that if I walk past you and you look at my watch, and we both happen to have atomic clock watches and we were watching super carefully, you would notice that my watch was running a little slow compared to yours. And I would say that since I'm entitled to be an observer and say that I'm stationary and you're the one moving, I'd say, no, it's your clock that's running slow. So this gets us into a bit of a pickle that gets called the twins paradox. And so we need to think about how to resolve it. So in the twins paradox, what we imagine is that there are two twins who we will cleverly call O and O prime. Initially, they were both going to be going on the same spaceship heading out to some star 10 light years away. A light year, by the way, is literally the distance that light travels in 1 year. So it is the speed of light times 1 year, or 3 times 10 to the 8 meters. Or we can say that this is 3 times 10 to the 8 meters per second, roughly, times a year is roughly pi times 10 to the 7 seconds. It's not exactly that, but it's close enough. So anyway, you get something just a bit shy of 10 to the 16 meters. But what's really handy is that you can then say the speed of light is 1 light year per year. So that's when dealing with astronomical travel, that is a very handy unit. So anyway, our twins were both going to go on the same expedition out to this star over here. And they would be going in a spaceship that could travel at 0.9 times the speed of light. Now, shortly before the launch window, one of the twins broke their leg in a skiing accident, and they weren't permitted to join on. Someone else did in their place. But what that means now is that the twins are separated. One is going to remain on Earth while the other one travels back and forth to the distant star. Now, it turns out that perhaps the twin that got to stay behind on Earth, that things actually worked out okay for them. Because what wound up happening is that the spaceship traveled out to the distant star, and then it turned out that the inhabitants of that distant star made it abundantly clear that they didn't want any visitors. And so the starship just had to immediately turn around and go back home without even landing or anything. So that was a lot of time in the starship. So let's start to figure out how long, in fact, this is going to take. Well, for O here, O is going to say that this round trip was 20 light years, or that each leg of the trip, let's call this leg 1 and leg 2, would take 11.1 years to do, because 10 light years over 0.9 c, that's going to work out to be 11.1 years. So the dilated time for leg 1 is 11.1 years, and this is because the spaceship is seen as moving. And similarly, the dilated time for leg 2 is also going to be 11.1 years. So, back here on Earth, they just said, hey, out 10 light years at 0.9 light years per year, 11.1 years out, 11.1 years back. So, definitely aged 22.2 years. Now let's go and think about this from the perspective of O prime, our twin who actually did go on the rocket journey. First off, if you do the length contraction calculation, what you will get is that O prime is going to say that the distance between the stars, because remember, the twin on the rocket ship is going to say the sun is moving away from them and the star is moving toward them on the way out, then on the way back the other way around. But either way, that twin, when you do the relativistic, when you do the length contraction calculation, that twin is going to say that there are 4.37 light years between the sun and that distant star. Now, that twin is going to be measuring the proper time that it takes, because first the twin will see the sun where the twin was at, and then the distant star. Since it's the same location, that's a proper time interval. Well, we can work out that proper time interval. 4.37 light years divided by the speed of light, 0.9 light years per year. That is going to take 4.85 years. And same for the return journey. The twin is going to say that took 4.85 years for this star to move away and for the sun to get back to that twin. So if we add that together, we get that O prime aged 9.7 years. So 12 and a half years different, quite a bit. So what's going on here? Couldn't we say that, but wait, you swore to me that O could say they're stationary and that O prime is the one moving and that O prime's clock should be running slow. So then wouldn't we say that, since definitely O prime is convinced that they age 9.7 years, wouldn't they be convinced that their twin left behind on Earth aged even less than 9.7 years and then back and forth? So we have to break that paradox here. And so it turns out that one of the key assumptions of special relativity is that you are an inertial observer. That means that you are not accelerating. Now, one of these twins is inertial and one of them is not. Which twin is not inertial? Pause the video and get back with me. Okay, so O prime is not an inertial observer. At points A, B, and C, the twin had to accelerate. First to go from 0 to 0.9 C to the right, then to reverse course to go to 0.9 C to the left, and then finally to come again to a halt to meet up with their twin back on Earth. That's enough to break the symmetry, just the fact that these 3 accelerations happened. And that's enough to say that now O prime was definitely the one that aged less. But, you might say, surely we could imagine that the rocket got up to 0.9 C very quickly, so quickly that over 4.3, over 4.5 or 5 years or whatever, that amount of time basically didn't matter worth a hill of beans. Okay, I'll go ahead and grant you that. But then the thing is that O prime was first moving to the right at 0.9 C, and then they were moving to the left at 0.9 C. So they actually occupied two different reference frames during the journey. And that's also enough to break the symmetry. In fact, a calculation that you can do is to just say, let's imagine that O sent out a birthday message by radio every year to their twin on O prime. So on the way out, the birthday messages will be sent once a year, and they would be traveling at 1 light year per year. Now to O prime here, they would say, okay, that's all well and good. But then that means the second message, O was a light year, was 0.9 light years further away from them. So when you figure out the fact that O prime says that O is running away from them, and so that each subsequent birthday message takes longer to get to them, you would figure out that on the outbound trip, if we do fractional birthday messages, O prime would receive 1.115 birthday messages. Now, O prime would say that O was turning around, but now O is sending messages, is catching up to their messages. They're traveling toward O once at 0.9 C, so they're only getting a little behind their birthday messages. So when you work it out, what you get is that in that interval, they'd receive 21.188 messages. Added up, it works out to be 22.2 years. So that's how we resolve the twins paradox. You can only do meaningful comparisons of time when two things are in the same reference frame. O was first in the frame of the Earth, then in this frame to the right, then this frame to the left, and then back to the Earth. By jumping all the frames, O prime did that. So by jumping all the frames, it meant that O prime was the one that aged less. Now, a related kind of phenomenon to this is what's called the relativistic Doppler shift. Or Doppler effect. So if you remember from mechanics, the Doppler effect for sound was like, if something's moving toward me, the pitch goes higher. If they're moving away from me, the pitch goes lower. If I'm moving toward them, it's higher. If I'm moving away, it's lower. It's a little different here. So let's just imagine that we've got some star here, and you are in the frame of that star. So you will see wavefronts of light emerge from the star. So I'm just going to mark this off as one wavelength here. And in all directions, you would say, S here would say that the wavefronts are propagating at the speed of light. Now, let's say that you are S prime, who is seeing the star S approach. So then, similar to what I was just discussing with the twin, the first wavefront would have, S prime would see the first wavefront as having been emitted from here, and the second one from here. this distance between where the wavefronts were emitted would be v times the period as s prime would see it. So I'll call that t prime. And then they would measure this shorter wavelength here. We'll call that lambda prime. So here we can observe that this wavelength here would be equal to the speed of light times the period in the proper frame. So lambda prime will be, well, in the dilated frame that, would be c t prime, what you would get if the source weren't moving. So this distance right here is c t prime minus vt prime, like so. And then we can also remember that the frequency times the wavelength is always equal to the speed. Or this will give us that the frequency detected by s prime would be the speed of light over lambda prime. Okay, so putting that in, that's going to give us c over c t prime. Oops. T prime minus v t prime. Now, to take that to the to compare t prime to what s would say, t, we would be going ahead and timesing that by gamma, right? So this is going to be c over gamma c, gamma c minus v times t. All right. And then you can say, oh, wait, but 1 over t is the frequency. If you rearrange it and make it all pretty, so here I'm just going to skip some steps for just a moment here. What you get is that f prime here, which we'll now just say is the frequency that the observer detects, will be equal to, after you rearrange this all around, 1, this is putting in for gamma and everything, you get 1 plus or minus v over c, I'll get into the plus or minus in just a second, over 1 minus or plus v over c, times the frequency of the source. Now, if the two things are approaching each other, you use the upper signs. And you use the lower signs if they are receding from each other. Which that would have come from me looking at the other case where we're going the other way. That would have put in a plus sign here. So this is a little different from the Doppler effect for sound. Because remember, with sound, there is a preferred frame of reference. You calculate everything in the frame of reference of the air. So this meant that for sound, you had to worry both about whether the source is approaching the receiver, but that might not be the same thing as whether the receiver is approaching the source or not. So for the equivalent expression for sound, you had 4 possible combinations of plus and minus signs. Here for light, you've only got the 2. If they are approaching each other, it's a plus sign here and this minus sign there. If they're going away from each other, it's a minus sign here and a plus sign there. So what that means is that if the source and the observer are approaching each other, this will be shifted towards the blue. So we call this a blue shift. And if they're going away from each other, then we're going to go to lower frequencies, and this is a red shift, longer wavelengths. And by the way, this is how we've been able to detect most of the planets we know about. Of course, the 8 that are right next to us in our solar system, we detected either by living on them or looking at them, either with the unaided eye or possibly with telescopes. But what about all those gazillions of other stars out there? One of the techniques that's used is, let's say this is some distant star and it has a planet orbiting it, preferably a pretty good sized one, like think Jupiter or something. Well, it's just a matter of just how sensitive you want to be in doing your observations. So let's say the planet is going around like this and you are over here looking at it. What's going to happen is that the planet and the star don't actually officially orbit each. The star doesn't perfectly orbit the planet doesn't perfectly orbit the star. Instead, both the star and the planet orbit about their common center of mass. If you were to imagine putting them on a teeter-totter, oops, I should have it shifted over here. There's their common center of mass. So if you were to put the two on a teeter-totter, this would be the point where you would put the fulcrum of the teeter-totter, so the game of teeter-totter would be fair. And so what happens is the star actually orbits around this center of mass in a very tiny orbit with the exact same period as the planet in question. Now what this means is that for half of the orbital period, that star, if everything's lined up right, could be approaching you, in which case you would see the light being a little bit blue shifted compared to the typical spectrum of the star. And then when the star is going away from you just a little bit, the light will be just a little bit red shifted. And so by watching over a few periods, you can see this oscillation between red and blue shifts, and that's enough to detect the planet. In fact, that combined with using spectral properties of the star to figure out things about its mass is actually enough to let you figure out even how massive the planet in question is and how far away it is from that distant star. Alrighty, so in the next video I am going to do a revisit of the Lorentz force law, this time using length contraction to arrive at it. Catch you over there.